So what I'm showing you here, this is a server that I have at my work. It has almost 400 gigabyte RAM, and it has 64 cores. But you see, it also runs Ubuntu, and I can, it's very fast in visualizing data. This is Canada, and this is Sentinel-2 data. It's fantastic data. And so I made the R code to download. You see, I made the styling system, and then I download Sentinel data for whole of Alberta. We have a project there, and then we're going to do predictive mapping for using Ensemble Machine Learning, of course. But just to give you an idea, when you start doing some serious work, yes, you need to invest a bit in hardware. Why do I need 400 gigabyte RAM? What do you think? Well, I mean, when I do training with serious data sets, like 100,000 or 200,000 points, or once I did the 5 million points, and I have 300 covariates, just the regression matrix is few gigabytes. I only work with the raster data. There's no, well, points are okay. Points are like a table, basically, a matrix. But anyway, so then you do have to invest a bit. But just to give you an idea, when it's like a serious project, and also I can show you this. If I have this thing here, let me see. This was the histosols of the world. I'm trying to show you some more serious data set. Yeah, so you see, these are the more serious data sets where you recover like 100,000 points, and then you do modeling with the Ensemble Machine Learning also. And then to fit a model, I mean, I would leave this, even these 64 cores, they will run for 1 hour or maybe 2 hours to get the models. So it can be quite computational. What did I want to show you? So when I was looking at this machine learning, and especially because I find this interesting, when you do these errors from machine learning, so you get like this thing, right? So what I realized, so question is, this is the model error from Ensemble, and question is, where would you go and sample here? Where would you go and sample? If I told you I want to improve the map, I have some little budget, so I can only sample like, for this map, I can only sample like 50 points. Where would you go and sample? Yes. Yeah, but it's also because you see that the highest error, no? Like, I mean, if I see here the like low errors, like, would you go and sample again here? You say, well, it looks fine. Let's go and sample here. And so you could randomize a sample where the probability of taking another draw is proportional to the error. So you do a random draw, but for every pixel you use a probability based or weight based on the error. And what will happen then? Most likely, you will decrease the so you will increase the accuracy of this map, and possibly that's the fastest way to decrease the accuracy, right? If you just randomly pick up points, you're not going to increase much accuracy, most likely. But if you put the points where you have the highest errors, you know, which are very distinct with machine learning, then you have a better chance to, like, with a minimum number of samples, like, decrease the errors as much as possible. Anyway, I was thinking about this. Herod might not agree with me, but I was thinking about it, so I thought that like what could be a robust way if you want to start a new predictive soil mapping project. So you start, you know, new project. So then I would advise like a two-stage project. Two-stage project. And first stage, you take a minimum number of samples, so you save the cost, and just enough samples to get the first estimate of the map. Okay? Once you get that first estimate, you estimate this prediction error that I just showed you, and then you take kind of engineering approach, and you say, well, we want to drop this RMSE up to here. And let's say if you have some function that allows you to estimate how many samples you have to collect, and then you go and sample proportionally to the error, and then you recompute everything. But this is a theory, so it needs to be proven whether it will work. What do you think, Herod?
I agree, but it's not new. I mean, this two-phase or multi-stage sampling is very well known already. I mean, like...
And you go and sample where the errors are the highest, the prediction errors are highest. Is that the...
Okay, so it's more like in the past they did things like, you know, when it's of course more geostatistic-based than machine learning, but like, okay, first you go into the field to collect data to estimate your semi-variogram. Then given the semi-variogram, you can calculate what your grid spacing should be to get a certain accuracy in your desired in your map.
Yes.
And that's then what you use in the second phase.
Yes.
Because the kriging variance does not depend on the data.
Just on the distance, yeah.
On the variogram and on the something.
But this, in this case, the errors can be local. I mean, you can have a local places.
With the same way with the regression kriging, you can also have that.
Yes.
Yeah. But two-stage sampling is
known.
Quite common.
Okay.
But your process needs to be static. If you're looking at the nitrogen level, that's nitrogen, the nitrogen content of the soil. That's a dynamic sort of property. It changes over time. So if I go and do the mineral function right now, and then just like a few months on that.
All that we are saying now is about static.
Yes, yes.
But
for temper.
That we also work on space-time dynamic soil properties. But yeah, then if you say, let's go back 1 year later, but it changed a lot, like soil moisture, you cannot wait a few weeks to go back, right?
Can we enhance this to your space-time sample?
Nitrogen.
You're just using it at the time.
Yes, you will have the space-time errors, but they might be different through time, so it becomes more complex. Where do you sample it then? Then you have to aggregate through time, and you say, well, through time, on these places always have high errors, and then you go and sample there. But yes, but it's a bit more complex. But it could be that it's possible. Yes. Okay. So that was this thing. Now I want to show you some ensemble machine learning. Ensemble machine learning. I will start with the frameworks, and then I bring you to this landmap package, which is a wrapper for all this stuff. So the first thing that I worked on was I looked at the. Let's see this one. So first I looked at the H2O Ensemble. I'm not going to run it because I have to load things, so I'll just tell you about it, and you will see how it works. It's a similar principle for the other packages. So with the H2O, you can do Ensemble. There's the H2O Ensemble actually package and a function. So how does it work? Well, you specify the cross validation. So you say 5-fold. So here I say it's a 5-fold cross-validation. And then you specify the X and Y. X is the predictors and Y is the target column. And then you go and it will do like with cross-validation. And then you can also calculate this performance of Ensemble. So that will give you the estimated mean square error of the Ensemble predictions. And I use two models here. So you see this is the one error for the one model, error for the second model, and this is the error for Ensemble. And you see it's a bit smaller. So the two individually, they are weaker than the Ensemble. But it's just a small difference. And so that works fine if you do the H2O package. And I did it also for the second variable. Then I didn't get such a big difference, I think. Let me see. So the Ensemble was 0.75. No, it's still better. It's still better. See, here I have several. You see, that's the deep learning. Deep learning is available in H2O. And so you see, if you do Ensemble, you have a proof. You can prove it with the data that you will increase the accuracy. Going from the best predictor, which is random forest here, you can still push the accuracy further for a few more points. What would you do when you look at these numbers? Would you invest in Ensemble? There's an increase of, I don't know, like 5%. Is it worth it? If it's not computational test, it doesn't cost too much. If it costs you $10,000, or I don't know, to compute it, then you probably, I'm not sure, 5%, it's not worth it. But if it's just like 5 minutes computing, in this Ferrari machine I showed you, see my Ferrari computer, like Ferraris are not meant to sit in the garage, I need to drive it. So then I put and poof. Then the other package I showed you, this is a super learner. And super learner is I like the super learner because there's a nice documentation, there's a book, and there's also tutorial. There's a nice super learner tutorial, and it explains all the nitty-gritty stuff. So I actually never had to contact the authors. So this one. So I never had to contact them because I would just look at it and I say it's so well explained, So how do I parallelization? How do I classification? How do I compare multiple models? How do I find out which models are available? It's all here. And so that's why I started using the super learner. And this was the example, this one here. So this is with a super learner, and what I discovered, super learner is also very nice. You do everything in one line. You can also parallelize, you see, you do parallelization. And you can also say that this cluster, CL, sorry, not cluster, that's further. I do ID column, and in ID column I can, for example, leave whole profiles out. Okay, so you can also plug in the ID column, which is the unique cluster, and so it means it's not the same points will not be used for the bagging and for the fitting of the models, and that gives you then it protects you from this overfitting, especially with the soil data. So in this case actually it's a very nice example. In this case, I ignore that there are profiles. I ignore that there are profiles. And what happens, the XG boost, you see it has the lowest RMSE. It looks like it's way the best. Right? You see it's lowest when I do the XG boost. And if I ignore the locations. And then in the next example, I add the locations. Oh, first I subset, First I take this, the ones which are too high, I take them out, and I subset to these 3 models, and then I add the ID. Yes, you see the ID, and ID is the profile ID. Okay, so I add it in the super learner. It's all in one line. It's beautiful. So you say, these are the points which are clustered. You say, these are my covariates. I want to parallelize, and I want to use, I don't know, 5, 6 models. And you do everything at once. And now what happens that the XGBoost is one of the worst. It's not anymore very small. It's one of the worst now. And so this is the danger of machine learning if you use it blindly. I mean, if you look at the difference in the code, the only difference is that here I have the ID of the profile. Okay? And if you don't understand what happens there, yes, it will be like a black box for you, and you will get some results, and you will present it, and then they will find out that these are not realistic results. And that's what happened to me. That's why I'm doing this workshop. I don't want that you go through the same mistakes as me. The idea of a social culture is when you have experience and you learn a negative things that you share it so you don't have to repeat it. So just plugging in the ID, what happened in the XGBoost is the worst. I mean, it's not way the worst, but it's, the number is much higher now. The number is not 0.07, now it's 0.19. So the RMSE, this is, by the way, the pH in soil. So pH in 3D, right? So they had a soil profile data. Let me see how many points. Let me see, where is that? So 369, yes. 369 points. And then you block, you subset by the profile ID. And that means during the ensemble fitting, it's not going to take the same horizons for fitting of the model.
The same profile or the same horizon?
No, the same profile, sorry. And so then you get this final model, and then you do the prediction in 3D. So I just have to loop. I have depth at 10 centimeters, 30, 50, 70, 90. So, and then you loop, and then you predict, and you get this thing. And you see the pH really changes. I mean, if you go from 10 centimeters to 90 centimeters, it goes from, I don't know, 4.5 to 7. So it really changes in this study area. This is somewhere in Idaho, I think, or in Washington State, the Cook-Far data set. So that was the super learner. And then there is also the MLR package, make stacked learner. So it's not called Ensemble anything. That was I was looking for Ensemble, but it's called make stack learner. So we can just run it quickly just to see. I'm not running it now with the soil data. I'll just run it for you so you can see how it works. And it's a bit different than on the subsample and super learner. So it's a different way how people program. So how does it work? This is a classification task, right? So we say make a task, TSK. You see, this is not without coordinates. I'm just showing you. And then you say, I want 3 models, RPart, LDA, SVM. And then L applies to create learners. So you create with L apply, if you had here 50 models, with L apply, you just make 50 learners. And then we want to do probabilities. And now it's all defined. Now everything is, all the parameters are defined, and now I do train. Train is now fast, but if I run it with some bigger data, training can take time. And then as the output of training, let me see if I print it out. Yes. So it shows like what's the output that came as a training, but just a summary, and then we can do prediction. Now, as I said, the data set is small, but prediction is So you see, for each class you get the probabilities. So there are 3 classes. There are classes of, I think, plants or some flower, and so you see there's a probability for each of the 3 classes, and then response is the most probable. Okay, but it's very elegantly done. I mean, you shouldn't have any problems to work with that, except you have to plug in that you don't want to use the profiles, and it's possible through the ID column also. So when I look at this thing, I think you can specify the ID column. Yes, I also don't see it. So that's the thing I'm now exploring. I want to see how do I do that, or is it to be the make learner? To plug in the profile IDs or the unique locations. Here, ID. So it's possible when I specify these IDs for all models, it's possible to add the ID column, which most likely will then subset based, for example, on profiles if we do 3D. So it is possible, but I do have to do some testing. To be honest with you, I just started working with MLR. I do see it as something that is very well programmed, and now they're making a new version. It's called MLR3, and it will be very highly scalable. It will be compatible with the future package, so it means you can also write in cloud.
Tom, you mentioned the super learner.
Yes.
Now you talk about MLR. They do the same thing basically, right?
Yes, but there are differences. People have a different ways they implement things, and also they look in different literature. The MLR, I think it's wider because MLR has also the super learner. So yes.
And the super learner doesn't have MLR.
No, it's a much bigger package. It's definitely. I mean, it's the MLR is something like 30 people developing, and now it's very intensive. And a super learner was like 2 people basically, right?
Will it still exist 5 years from now?
The super learner now, there's nothing much happening, so it doesn't mean it's a bad package. But some packages are so good that you don't have to really change much. You just leave it 5 years. But so I definitely think the super learner, the advantage is they write up the documentation. They have a book. They have a book about super learners, and they're from Berkeley, and it's really nicely programmed. You do in one line everything. But there are 2 people, and now I see over 1 year there was no commits on GitHub, so there's not much happening. While on the other side, the MLR, it's very active, and they are very ambitious. And so if you want to get into something ambitious and something that you can also influence tomorrow, then you should do definitely the MLR. This is the same thing, just with the regression. And you also do the prediction. But for example, what I discovered now, I use for my package, so I'm looking now at the landmap package. And so what I use so far, I use the super learner, because for example with super learner you can specify this meta learner, and then you get all the predictions. I don't have to compute them by hand. It's all implemented. So then I can calculate the model error. And that's why I find it like it's a bit easier. But I'm just checking with Patrick if I can do the same things, with MLR. It could be that I can do the same things. So I can show you now this package I'm making. This is the key function that you're interested in. That's something I just made recently. And so it's just a one script. It's maybe 300 lines of code. And this is where I do all the things for automated mapping. And I combine the variogram modeling, ensemble machine learning, principal component analysis, spatial cross-validation, all the things. Everything I knew, I put it now in one function. and I made it so it's like it should run like automatic. And also it automatically parallelizes and things like that. So this is as good as it gets from my side. But I will now also run one bit bigger data set, this SIG data set, just to show you, the computing intensity, just so you get an idea. This data set is, so if I look at this SIG data set, it looks like this. So I have the points and I have the grids, and I will just plot one. So I just plot the Swiss 1K, the first layer. So it looks like this. This is a digital elevation model of Switzerland, right? And now I run this trained spatial learner running through the super learner, and I say this is the rainfall points. So let's try like this. Okay, so these are, you see this is the DM, and these are the points overlaid over the DM. And so what do? I say train super learner. You take the points, you take the covariates, and here I define lambda because I know it's a long normal variable. So when I fit the variogram, it will do a transformation automatically. Okay, so this is the only thing I have to define. That's it. And so, as I said here, that now what's happening is you get the principal components first, then you get the buffer distances. Buffer distance, you see how my computer is a bit sweating, right? You see how it's running in parallel, so it's using all the cores, but it takes time because there's 360 points. So I have to calculate 360 buffer distances in 1 kilometer. And then now he's fitting the super learner. You see again fully parallelized, running all the cores. If I will run it on this laptop, the Windows laptop, we will wait for 5 minutes. It's not worth it. Here it's done in maybe, how much I'm running now? Maybe, so it took about 40 seconds, maybe a bit less. And you see these are the standard steps, and then you just say predict. It's a really automated mapping system. I mean, basically, when you think about it, I only specify the lambda with 1, and only because I want to get the variogram. That's not for the machine learning.
Is there any way to avoid the buffer distance calculations if you're using a larger data set?
Yes, sure. You can. It's explained, but so you can say, for example, you can say buffer dist. Buffer dist is equal to null. Then it's not going to compute it at all. You can also say we are factor. You can also say don't take buffer distance to every point, but group the points, and then it will calculate buffer distances only for the groups of points. Then you get much less buffer distances.
So Tom, can I ask you a question?
Yes.
Before you said, I want to share with you, I made mistakes in the past. I did a cross-validation, not leave profile out, and so I got it wrong. And you have to really know what you're doing when you do this kind of stuff.
Yes.
But now you're also building functions that are wrapper functions that do everything in one go.
Yes, yes.
So that is very risky from the point of view, like people want to know what they're doing, right?
Yes.
So what is your viewpoint on
that? Yes. So yes, it's a very good point, and it looks like I'm contradicting myself absolutely, which I do often. Yes. So one more time, I think I mentioned that, but I'll say one more time, I'll emphasize. I think for the way I see machine learning, yes, you can automate a lot of things, but you should be aware what you're doing, and you should invest much more time in post-model diagnostics. And now I don't have that code to show you that, right? But variable importance, partial correlation plots, zooming on the individual points, looking at the errors, why they're high, and things like that. And then you become aware, and then you feel like I'm aware what's going on with this, how this model works. I mean, eventually, it's this plot I showed you. It's kind of one of the most important plots is this thing here. This is where the soil scientist comes in, and it is very important that you see that this machine learning with soil organic carbon, you will make an error here. It's just it cannot happen. So machine learning makes an error. Yeah, it's not because it has like 2 points, right? And it goes around 2 points, and maybe there's not many cases where you have a high soil organic carbon, but it's a good that you visualize it and you do this diagnostics and you understand, and then you understand why is it going up again? Why does this go up again? Just because it has very little points and 1 point by accident is higher. But yes, I am a bit contradicting myself in a sense that I want to make for people wrapper functions so they can get very quickly. They can make maps, and most likely many people will use that wrong way, and they will create artifacts. Yes, but
so why do you do it?
Because I want to help people automate the things that you can automate. The things you can automate, you should automate. You shouldn't. If you need to do fine tuning, and if you know that you can automate it, don't do it by hand. No, automate. I have to become a better programmer. I have to make sure that when I do model building and the spatial cross-validation things, that I also program it in a way that people don't make mistakes and then don't create artifacts and things. So I have to also think, how do I prevent that?
Then we should document every line.
Yes, I don't know. I mean, I assume there are people, not all users are the same. There are some users that actually are not interested so much in the mapping exercise. Some users are interested in using that maps to make some decision. And then some users are interested to make that map, understand how the map is made. And it's no problem. Like my code, you see all this code here, it's all open source. So if you say, well, I want to see how you did it, I mean, it's all documented. I even put comments, what I do. So, I mean, it's not that it's like behind, like some commercial software that you click and you don't know, right?
In principle, you can go back all the way very deep, so what's actually happening.
Yes.
But that may take you ages.
So if you are if you're interested in more advanced stuff, then I recommend that you look at the source code of the package, and then you can run things line by line. But if you are interested in just to get the best map and to employ the machine learning algorithms, then you should look for automation. So this is the machine learning just in a single function, and it's not cooked yet. So if you use it, if you download it and you use it, be careful. But I think in a couple of weeks, I have to just check with Patrick. Most likely, I will switch to MLR, and I'll leave the superlearner as the option B. And once I switch to MLR, I will make it all very nice, neat. So, and it shouldn't lead to error messages in Windows and things. So I will check all these things, and then it will be ready for use. So that's, I expect about a couple of weeks, yes. Then there was also for the soil types. This is with soil types. I have an example with binomial variable. Let me see. The binomial variable, I have to actually say that it's a binomial variable. So this is not automatic. I could test it. You can find out whether the variable is binomial or not, Probably not very difficult. And I also noticed when I did the prediction for binomial variable, that's a bit the pattern is a bit because of these distances. So we can discuss that. Let me see, where is that? So here, when I do binomial variable or when I do factors, so each class you get a probability. And what happens? You have this individual. Do you see these individual pixels where you have a? Oh, I have to turn this. Let's see. Well, let's calculate it. Look at the superlearner, MLR especially. I'll send you the slides, by the way. But look at the MLR. It's really a group which is ambitious, and they are doing a lot of things. And they're in Germany, they're Germans, so they always make the best products, right? So look at the MLR. These geographical distances, I think it's a new thing, relatively new thing. I know that Thorsten Behrens also, he published a paper with colleagues. They use even like the distances to the corners of the feature space of geographical space, right? So they look at the corners and they look at the distance to the center of the study area and things. I don't know if I wouldn't use all these distances. I definitely don't want to use the coordinates because I think they lead to these blocky structures, and it's really sensitive if you have open areas. And yes, it's a bit scary how much you could automate, but that doesn't mean that we should stop sampling. It just means, I think this two-stage sampling, I would like to do that more in future. I don't have at the moment budget to go and test that, but I have a feeling that could be, if somebody wants to do, I will be very interested to contribute. So you do this two-stage modeling. The first stage, you build up an initial model, you estimate where the errors are highest, and then you sample where you have highest errors, and then you see whether your total errors are like really rapidly decreasing. And if this working, you're really onto something. And then you can go next stage. So not only 2 stages, but you go third stage, and then you stop once you say, okay, now the accuracy of the map is good enough for application, and then you can stop. Maybe that's the way to make the predictive soil mapping also most cost effective, because I saw many projects, they just go and collect 50,000 point samples. And what's the justification? Why 50,000? Oh, because we need so many samples per hectare. But that's not a statistical justification, right? So that's why I tell people, instead of doing 50,000, go and collect 300 points and build initial models. And then you go and you say, we want this accuracy. And they say, well, then you need 20,000 more points, or maybe we need 100,000 more points, right? And then you add these additional points. And then you rebuild it, and you see whether you need another round. Yes, it's a wrong message if you think I make a function and in one line you do automated mapping. It's a wrong idea that if you think that, okay, now I don't have to learn statistics, forget about kriging, variograms. I do still fit variograms. The land map is going to fit variograms. It's going to do spatial cross-validation. I'm going to use the state-of-the-art geostatistics. I will still do variograms. I'm not going to do much kriging except just for the baseline comparison. But of course, my interest is to enable this ensemble machine learning for spatial mapping problems. But that's for you. It doesn't mean that you have to drop. Actually, I think that machine learning and statistical machine learning, they're just a higher level complexity. So it means it's not that you have to do less, you have to do more. So expect that you have to go back to your statistics books. Even you see Herald, which is like one of really the brightest statisticians I know. When he looks at some of the papers that people make in machine learning, he looks at it, I'm not sure what they do here. because it's a mixture of computer science, statistics today. It's complex. There's repetitions, there's like different learning algorithms and things like that. So it's complex. So you have to get yourself to a high level. So these are my conclusions. Thank you for your patience. It's not easy to follow things on Sunday, so I appreciate that. And I will continue developing this. If you have some data, you get some map, or you discover something, send me an email, no problem. And I will send you all the links to the videos and all the materials as soon as we upload them. So you can come back and you can test yourself some things. Yes, 5:30 we start with the reception. Are there any more questions or comments? Yes? Most of stuff I use in the landmap, it's all C++ based. The XGBoost is C++, the Ranger is C++, and the KSVM, I'm not sure, but probably. MLR, the new version, MLR3, I don't know why they call it 3. Maybe they have a 5 that they want to skip 2. But you can read about MLR3, and it's so it will be faster, and it will build up on top of the future package. The future package is the like high level parallelization programming that allows you in a cloud. So if you buy a cloud computing, you don't have to think much. You say, this is my server, this is my login, and you say, and you compute very quickly. And then it just questions how much you have to pay to compute. But it's not that you have to set things and connect. And so the MLR will work at that. So then you will have your laptop, and you put your parameters on your laptop. You say, this is my data, but it's very computational. And you will just say in MLR, okay, these are my parameters, connection parameters for the server, for the cloud. And then it will send it to compute in 1 minute and send it back. And otherwise you wait for half day. Yes.
I have a more general question. As a graduate student, I'm investing a lot of time learning R. Python is another programming language that kind of really comes to the forefront. I read a paper last week and kind of documenting the changes in research, specifically what programming languages use, and you're starting to see that more articles are being written with Python than R. So do you, for someone like a graduate student, what do you think about that?
No, Python is much bigger than R. I mean, everybody knows that. It's much bigger. It's easier to build up things. It's like also, R, it's like it's not optimized for computing and for matrix solving. And so on one hand, you would just say, okay, just keep it, learn Python. But R has many things that Python doesn't. Many things. So like geostatistics, spatial data, statistical tests, Python doesn't have. So then people in Python use R also. I know that they load libraries. In Python you can load R, right? And there is a R package now, Reticulate, which is a wrapper for Python, and so it will do Python calculation, and you get back R objects. So the integration is seamless, but in theory it's seamless, but in practice, then okay, it's some things can be cumbersome. My suggestion to you is learn both. Yeah. There was a question about Julia, which is another program package, and this one has apparently more efficient matrix calculation, and there are some other things more efficient. And I read about it, a blog, and then some people say, yeah, you use dominantly Julia if you want. But then some people, no, the community, like when I look at the R spatial, it's a very productive community. Every year they make new things. It's a live support. When you ask a question, you get very quickly. And Julia doesn't have that. So, I'm not convinced. I'm not going to now move everything to Julia, migrate, But both Python and R, absolutely learn both. Both Python and R, it's and they can be easily combined. So, you know,
Well, I know all your tutorials are in R, so I'll use it in R.
I like. I have now. I was doing this package plot.kml to generate KML, and I develop it very easily because there's a nice guy from I think Berkeley. He made this XML package, and then I could easily program because it was XML functions, and you know I could figure out things. But then I saw it in Python. There's the same XML. So when I told a colleague I needed some KML conversion from the Geo server, and he says, no, I do it in Python. I'm faster in Python. And then I saw, but it's similar. You know, it's not that it's now like you have to make less code or something. I mean, it's similar. You have the you load objects and you run some functions and you can loop and you can, so it's many things are similar.
I think we should stop.
Yes.
We'll be around the whole week, Tom as well. So